Hello and good day to all of you. So I'm here today to discuss the problem solving for balanced polyphase systems under the topic of or the subject of polyphase systems. So before we proceed with anything else, if you want to have the copy of the problem, you can go to the description link or tab, and then there is a link there that has all of the main problems on this topic and its corresponding supplementary problems for you to solve. Okay, let us read the problem first. So this is a very good problem. A phase voltage of 230 volts, three-phase supply, feeds a balanced Y-connected load, which has a value of 10 plus J 5 ohms per phase. We need to get the real power of the system in watts. Okay, first of which is we are given a 230 volt, but there's no vector involved. When I say vector, it must have a magnitude and direction. If this is the case, if the system is balanced, we can assume the following. Okay, first assumption is you can have the voltage at AN as our reference. Please take note, phase voltage for balanced polyphase systems. And another assumptions that you can use is an ABC clockwise or positive sequence. If there's no sequence involved, we need to have an assumption of a positive sequence. Okay, in which the problem states a phase voltage, which is, we can assume that is at phase A to N. Okay, this is your VAN. So that is 230 bar 0, which is based from our assumption. And then it will followed by VBN, or rather VBN here, and VCN respectively. So in this case, you need to have a lagging of negative 120 for VBN and positive 120 for VCN. You can recall the phase sequences on our last topic, which is very important now for the application of balanced polyphase problems. Okay, since we already have those voltages and the corresponding sequence, now we need to draw the corresponding power system diagram or Ph.D. And then you can have in terms of Y to Y. And please take note, we can simplify more the things here on the single line diagram to a per phase basis that we have discussed from the basic fundamental of this topic, which is balanced polyphase. Now you have here your terminal points, so please take note that some of our problems will be simplified using these terminals only at A, B, and C. Okay, this is terminal points. Okay, now we can now have the per phase analysis of one phase of the system. I could say phase A, simply to have a AC circuit, and we can now do circuit analysis on that per phase basis of the problem. So we can have one phase of the system. I could isolate this here and it will become like this. So please take note, you have your ground here, neutral wire. Okay, since balance, IN is 0, IN is 0, so the conductor is open. So this is your ground here, your common ground. Okay, ground, ND. ND. So hence, taking the per phase basis, you have the 230 volt here, bar 0, which is your VAN. One phase of the system, 10 plus J5, since balance, you have the same impedances, and IA alone. You can also take, if you want, phase B of the system. Okay, so if you take the PPA at phase B, it will become like this. So this is 10 plus J5, and then you have 230 bar negative 120 for VBN. So plus minus. And if you want to get directly the current IB, because the only difference of IA, IB, and IC is 120 degree apart, they have the same magnitude. Okay, so if you want to take at phase C, you can do the same thing. So this is the advantage of having per phase basis. Since they are balanced, the only difference is 120 degree apart in phase displacement. So we can now use at phase A as our main goal here, since our problem is just getting the total power. So using Ohm's law, you have 230 ohms, 230 volts divided by 10 plus J5 ohms. You will have 20.57 negative 26.565 degree amperes. Okay, now since we're dealing now with powers, the only difference with the single phase is you need to multiply it by 3. So it means if you have a complex power S and you want to get the total in a three-phase system and you have a single phase power, I could say S per phase, you just multiply it by 3. So it means if you have a complex power at A and B and C respectively, you just multiply it by 3. Okay, so for this we multiply it by 3, and using the fundamentals of circuits, I squared R. Okay, and this R here is your R load. By the way, where is R here at the circuit? As you can see, you have the real part R and the reactive part X. So it means you have the real part R, reactive part X. So just get the real part and the square of the current, and then multiply it by 3. You obtain this value of 12,694 watts. So here we explain the application of the per phase basis on polyphase system problems. And please take note, in order to have a per phase basis, it must be connected in Y. Y connected. So thus we can continue our problem solving on problem number 2. Hello once again. So we will continue our discussion on problem number 2 under the balanced polyphase systems under lesson of your polyphase systems or power systems 1. So let's read the problem first. Now, based on problem number 1, if the load is already reconnected to a delta connected system with the same impedance, we need to get the line current. Okay, so what I did is, this is the same diagram as before in problem number 1, but the only difference is the load becomes a 10 plus J5. Our main concern, our main goal is to get either of these currents, IA, IB, or IC. Okay, since our main objective is just line current, it can be IA, IB, or IC. So specifically, I will solve the current IA for this purpose. Okay, now there are many solutions for this problem. Okay, the first solution is you can reconnect the delta to Y by dividing 10 plus J5 by 3, and then use per phase analysis, get IA by using Ohm's law. That's the first. The second is we will stick to the diagram and we will make use of the fundamentals that we have learned so far on phase sequences and on this lesson, which is on the balanced polyphase system. So I think I will stick to number 2 first, so that you can see the formulas and their applications. Okay, first of which is we need to know what is the reference. The reference is VAN bar 0, which we already mentioned a while ago, that if there's no phasor reference, you can have VAN as our reference, and if there's no sequence, which is important as well, you can use the ABC clockwise or the positive sequence rotation. Okay, now we already established this from the first problem. 230 bar 0, 230 bar negative 120, and 230 plus 120. So we have no other problems with that. And then you have the terminal points A, B, and C. Okay, we have IAB, phase current at AB, phase current at BC, phase current at CA. Okay, recall. So it will ring a bell in that video. VL is equal to square root of 3. V phase, but always remember that positive sequence must lead by 30. Okay, in other words, we already described this one on phase sequence. So if you have a line voltage AB, it must have a phase voltage at A as well. Look at the first letters must be coincide or synchronous to each other. Since VAN is already defined as 230 bar 0, so just substitute it there, and then your VAB vector will have this value. Okay, so it is easy to understand, right? Now, talking about the phase currents that is flowing on this delta connected load, we can get one. Specifically this, your IAB. Okay, to get IAB, recall again, no, in a delta connected load, that the line voltage is also equal to the phase voltage of the load. Okay, so line voltage VL is equal to the phase voltage of the load. So hence your small letter VAB is also equal to the capital VAB here, which is phase and line respectively. Okay, so what we have already computed here, that is your VAB vector there, and then JB is the impedance per load, 10 plus J5. Okay, it will yield with this answer, but that is not the final answer because you just only got the phase voltage at phase A, okay, which is IAB. So, go back to the basic fundamentals again. So, we have an ABC sequence, another recall, another notification bell on the video that IL is equal to square root of 3 I phase in magnitude, but it lags by 30. Don't forget the negative 30 there, lags by 30 degree. Hence, we need to coincide this one in terms of letter IL is IA. The phase current is IAB. Yes, it must have the same letter here. Square root of 3 and then lag by negative 30. And please take note, this vector here is this value. So just substitute. The answer on this problem is 61.71 bar negative 26.56 degree amperes. So that is in degree ampere. So just get only one. Now there's another third solution if you really want to have another solution here. You can use the scenario wherein you can get VAB, which is VAN minus VBN. Since you have your VAN is 230, deduct or minus 230 minus 120, you got VAB. So you will have the same result here, this one. Okay. And then from there, you can solve the phase current at IAB and then use the relationship of this, and then you can now get IA. Or if you want to get ICA, you can do so by having the voltage at CA, you divide it by ZCA. And then you want to get IA in terms of IAB minus ICA. And then it will yield also on this answer. That's the third solution. So you can analyze that one if you want to have a grasp of the basic concepts. And if you already know that, those three solutions, you can solve any problem that you want. The answer is still the same. So we will go forward to problem number 3. Stay tuned. Hi and good day to all of you again. So let us continue our problem solving on problem number 3. Okay, let us read the problem first. A 220 volt 3-phase supply feeds a balanced Y connected load of 16 plus J9 ohms per phase. So the phase current at line B will be equal to blank. Okay, so this is the solution on that problem under the balanced polyphase system. So the most practical or the most convenient or faster way to do this is using at the per phase basis, and you will concentrate on phase B. Okay, I did not draw anymore the power system diagram, since you can recall on problem number 1 that we already discussed comprehensively how you will do the per phase basis. So we will use PPA at phase B. But before you do that, you need to know the reference first. The reference is VAN bar 0. And please take note on the problem, the value of 220 volt. A 220 volt three-phase, this is already automatic line-to-line value. There's no doubt about that, except or unless it is stated as phase voltage, like problem 1. But problem number 2, it is very clear, a 220 volt three-phase source, 220 volt there is a line-to-line voltage, but you do not know what is the reference vector. Before you attack any problems on polyphase systems, it is very clear that you need to have the phase vector. Okay, now, since no phase vector or reference vector, we assume that VAN bar 0 is the reference or the vector A. Now, ABC sequence or a positive sequence. So you already know that one on phase sequences. And thus, the 220, okay, that is in terms of magnitude, you divide it by square root of 3 to become phase. And please take note, we make use of this relationship in magnitude, divided by square root of 3, the line voltage, to get the phase voltage magnitude at phase A. Okay, you have 127.017 bar 0. And please take note, if that is an ABC sequence, the phase B will lag negative 120 from the respective vector reference. So you have negative 120 there. And thus, we have the per phase basis of B, and we already extract that phase. So 127.017, 120, this is your VBN, current IB, and this is your Z load. And please take note, if that is in per phase basis and there's no description, if that is delta or Y, you must assume that is a Y connected. So you have 12 plus J9. Hence, you can now get IB by Ohm's law, 127.017 bar negative 120 over 16 plus J9. The answer is approximately equal to 7 bar negative 149.35 degree amp. So very, very easy problem if you already know the concepts involved on balanced polyphase. Okay, we can now go further to the next problem. Hello once again. So we are on our next problem under the balanced polyphase systems. So let us read the problem first. A delta connected balance load has an impedance of 38.4 plus J 28.8 ohms per phase. It is supplied by a three-phase line voltage of 4,157 volts. Find the line current IB in amperes using a VAB as our reference vector. Okay, this is the solution on this problem. So what we have already discussed, that if you have a delta connected load, you can have it on Y connected load. So in order to do that, you need to divide the Z delta by 3, considering the load delta is balanced. So dividing it by 3, the answer here is 12.8 plus J 9.6. We're dividing it by 3, this value of 38.4 plus J 28.8. Also, it is not mentioned what is the sequence of the problem. So we use an ABC sequence or positive sequence. Okay, but here it is mentioned on the problem that let the line voltage at phase A as our reference. So, in this case, you have no other choice but to use the line voltage at phase A as our reference. So, let us go forward to the solution. This will be a straightforward solution. Recall that VL is equal to square root of 3V phase, but it leads by 30 degrees. And we need to have, in terms of the same phase and same phase in the same line. Okay, it means that you have the same phase on your line voltage and the same phase on your phase voltage. So you have VAB and VAN respectively. Now you can now compute for VAN vector. So considering again the value of VAN, it will become 2,400 bar negative 30. And you want to get the line voltage at B, you can do so. by having 2,400, but it lags by 120 degrees. So we have described or discussed this one from the previous lesson. And thus, the answer is 24 bar negative 150. Why we need to get VB? Because we need to get IB, and thus, we can have a per phase basis on phase B. So here it is. The per phase analysis at phase B. So we have this scenario here. Okay, I did not draw the whole power system diagram anymore because we already discussed that one on problem 1 and 2. So you have here your BBN. You have your neutrals, of course, and you have your IB, and this is your ZY load. Hence, again, by using a little bit of your circuits, Ohm's law, you have 2,400 divided by 12.8, J 9.6. The answer in polar form is 150 bar 173.12 degree amperes. So we will go forward to problem number 5. Hello, let us conclude our discussion on balanced polyphase systems, and this will be our last problem, which is a board exam problem. Okay, so this is the problem. A 230 volt 3-phase system supplies a balanced Y load of 12 plus J 8.4 ohms per phase through a feeder having a resistance of 0.5 ohm per phase. Find the line current in amperes. Okay, we have here a scenario wherein there's a transmission line impedance. But again, the analysis is still the same. As long as you have the per phase analysis of one phase of the system, then you're good in then you are good now to solve the problem. However, we need to have some assumptions. First, you need to have the VAN as a reference. So if you have a 220 volt here, you need to divide it by, or divide this by square root of 3, and then you have the bar angle 0. So this will be your VAN, which is our reference. So you need to divide by square root of 3. And then there's no sequence, so we can have the ABC sequence or positive sequence. Okay, now we have here the feeder impedance or feeder resistance, 0.5. You do not need to multiply it by 2 simply because this is a per phase basis, so we need to have the per phase feeder resistance. So we have that as 0.5. And thus, having the per phase analysis of the whole system, I did not mention again the power system diagram. We have this power system, the PPA of problem number 5, and 220 over square root of 3 will lead to an answer 132.79 bar 0. So here it is. And then this is your Y connected load 12 plus J4 and your feeder resistance. Now, again, this is a series circuit again. So you can now get the line current by dividing 132 bar 0 all over 12 plus J4 plus, we forgot to mention the feeder resistance, 0.5 rather, 0.5 ohm resistance. So you need to add it up. And thus getting the numerical value here using your calculators, the answer is 8.817 bar negative 33.901 degree amp. And please take note, by the way, any phases can be used for the per phase analysis simply because we just need to have the line current value. Okay, this concludes the balanced polyphase systems. So what you will expect on the next lesson is the unbalanced polyphase systems. So that is also a good topic, and which is your preparation for power system analysis.